right, calculus friends, we're going to pick up from last time. And today we're going to be looking at volumes of revolution using the disk method. Previously in calculus, we had used our analytical methods to determine the volumes of solids when we had known cross-sectional areas. That was something like we'd seen here in the figure, where we were looking at all of these slices where we had these slices either vertical or horizontal or some other direction, and we were going to be creating a solid using these known shapes. Today, we're going to be forming solids when we have an axial revolution. That means we're going to be rotating around some fixed axis. So today we're going to start off, we're going to look at what we did last time, kind of review why we can use an integral expression to determine the volume of some shape, and then we're going to look at Desmos to visualize what we're actually talking about, and then we're going to create an expression. Why does this make sense? And create a process for figuring out the volumes of revolution. Well, here we can see we've got some shape going on, and we've got some cross-section. If we know the cross-sectional area, we're going to use our calculus techniques, where calculus, the integral, adds together a number of infinite pieces. So if we take the area of a single slice, give it some thickness, then we can go on to our definition of the integral, where we're taking that single area, we're giving it some thickness, and we're going to be evaluating from the left side to the right side. That idea of the area times the thickness, that gives us 3 dimensions. That's our volume. So we're going to be looking at this in terms of rotations now, instead of just this horizontal or unidirectional kind of sliding of the shape along the way. Here, let's go over and take a look at Desmos. All right, so in this example, we have the graph of the square root of x. So our function is going to be just the square root of x. I'm going to take this graph on the interval from 0 to 9, and we're going to rotate it about the x-axis. That's our horizontal axis. I want to think about how do we visualize a rotation. So here, I'm going to hit play on something, and we're going to see what happens. You can see that as the curve is rotating around, a rotation gives us these disks that are in the shape of circles perpendicular to the x-axis. Now, this is another visualization of that rotational motion. When we look at our curve, the square root of x, as we rotate it around, that gave us these cross-sectional slices that were all circles. We can find the area of a circle. Now, using our calculus, we're going to give that area, that disk, a small amount of thickness. You can see here, that's that dx. So as we look along the curve, as we go from 0 to 9, that disk is changing in radius. Now, the thickness is still dx, but what we can do using calculus is we can add together all of those areas with that thickness. Here, we've got one last visualization tool to show how we're creating this volume of a solid figure when we revolve around the x-axis. We've got a 3-dimensional perspective this time. So you can see that this curve, now it is a different curve from the square root of x, but we've got that arrow going around that our figure is going to be rotating around the x-axis. I'm going to hit play, and we're going to see how this solid is created. And we can see that when we rotate it around, we have these different radii that are going to form circular slices relative to the axis. We're going to use our calculus to take the thickness of those slices to find an integral that's going to add together all of those slices, thus giving us the volume. So here's our task: determine the volume of a solid when a curve is rotated about the x-axis. In the example here, we're going to take our square root of x, and we're going to go on the interval from 0 to 1. We're going to take that curve. Now you can see that we can always find the radius. The radius is going to be the height of that curve. I'm going to indicate that here. My radius is the square root of x. That is the distance from our axis of rotation up to the curve. That radius is going to be rotated about the x-axis, creating these disks with a circular cross-section. The thickness, you can see down at the bottom, is going to be our delta x. Now, we can find the area of a circle. Remember that the area of a circle is pi r squared. So then, if we're going to find the volume of one of those disks, the volume is going to be pi r squared multiplied by the thickness delta x. Combining this into our integral expression, we're going to be taking the integral of pi r squared dx, and our bounds in this case are going to go from 0 to 1. Now, we have that our radius is given by the square root of x. So if I combine these two ideas, that's going to rewrite our integral as pi times 0 to 1 of the square root of x squared dx, which is then pi times the integral from 0 to 1 of x dx. That gives us an expression that we can evaluate. That's going to be pi multiplied by 1/2 x squared, evaluated from 0 to 1, which then gives us pi multiplied by 1/2 minus 0, or our volume is going to be pi over 2. Now, the big idea here is that anytime we're going to be finding the volume of a solid, our volume is going to be pi multiplied by the integral from a to b, or times the radius squared dx.